Alright guys, I hate to do it this way, but because of snow days and 2-hour delays and me being gone one day, we are going to take a walk through lesson 5.1, exploration 1 and 2 this way. So this is the Can You Explain It from the opening of the book. And when you look at this photo, you start to see this dark spot that is in the middle of this bright red light. Something has to be causing that light. So think for a second, what do you think might be causing that black amongst all of that light that is being surrounded? You may already have a pretty good idea from reading your notes, but throughout this entire lesson, that's kind of what you want to come back to. What is causing what we are seeing? We want to find some evidence that can help us make a claim for this photo. Okay. We've got three very different objects, but similar purposes here. We've got a land-based telescope. You've got a telescope that is orbiting the Earth as a satellite, and then you have a space probe. All three of these objects are meant to give us information about space. However, there are limitations to each of these. The land-based telescope, you've got to deal with that atmosphere to be able to concentrate light, which is what a telescope is designed to do. That light has to pass through our atmosphere, which can greatly distort an image. The satellite telescope, limits the atmosphere distraction since it is above the atmosphere, and then that space probe is being sent out from Earth, but it has to communicate back to Earth. Are any of these better than the others? Each one has strengths, each one has weaknesses. They all serve a purpose for us to find out more about space. Okay, here is where we want to focus our time because this is really going to come into play over the next 3 weeks as you work through the lab. We're going to look at the visible light spectrum and light emitting different colors. So you've got your electromagnetic spectrum up there from gamma ray all the way to radio waves, and visible light is a very small purpose section of that. Okay, you've got from the short wavelength, higher energies, of the purple, to the longer wavelength, lower energy of the red. Now, what does wavelength mean? Wavelength is from crest to crest. So if we are looking at a wave, let's see if I can draw a wave here. Okay, this is a wavelength. Okay, your frequency is how often in a given time frame that wavelength occurs. So you can see over here, in a very small amount of time, you've got lots of wavelengths. It has a higher frequency, where if we look at that same segment over at the other end, you've got very few wavelengths. In fact, you don't get any in that spot. So make sure you know the terms wavelength and frequency. Okay, the image down here below is just to show you kind of what that UV light, we hear a lot about UVA, UVB, and UVC. Well, it's all part of this ultraviolet light. It's just how it harms us, what it does to our skin. Okay, UVC is the very dangerous, UVB can burn you, and then UVA is those tanning rays that when we all want that nice summer glow to our skin. Okay, so when you're looking for sunscreen, okay, if you see it that it blocks UVA or UVB or UVC, this is what it's talking about. UVA being, again, tanning, to UVC being the very dangerous. All right, here is the Messier 101, where it is taken via 3 different images. One is the X-ray waves, going back to our previous image. You see the X-rays over by the gamma rays. Okay, you've got your visible light, that's what we see, that Roy G. Biv, that color spectrum. And then your infrared waves, which are just to the opposite end. So this image is looking at X-ray, infrared, and then our visible light spectrum. So you can see how, depending on which wavelength of electromagnetic spectrum we're looking at, we can get very different images of the same thing. Okay. Here is, again, we talked about telescopes, we talked about that light passing through our atmosphere. Okay, when we're looking at the electromagnetic spectrum, okay, and this image is kind of flipped because you got gamma rays over here, okay, and in our previous image, gamma rays were over here. You can see how the atmosphere absorbs some of that electromagnetic radiation. And where? So as we go up, just so you can kind of see, this is altitude. So as we go higher into the atmosphere, we have everything passing through. Kind of that mid layer, you can see that there is definitely a difference of what's being passed through. And then at the very bottom, what are the things coming through? Ultraviolet, visible, infrared, and radio waves. Okay, so a very different snapshot of what parts of the electromagnetic spectrum we can actually receive at sea level. Again, plays a part in those telescopes and why some telescopes we need to launch, because we wouldn't be able to see gamma rays or X-rays coming through if they were at sea level. Okay, Doppler effect. What is the Doppler effect? You've heard the Doppler effect before. When you hear police sirens and fire trucks and tornado sirens, you hear that pitch changing depending on which angle the object is traveling, or which object, how you are traveling to that object. Okay, we're not going to play the video. You can go and look up the Doppler effect via Sheldon Cooper from Big Bang Theory and kind of his explanation of what that is. There's also a really good video that you could go look at for Bozeman Science about the Doppler effect. It really gives you a good perspective of what is redshift and what is blue shift, okay? Depending on, is the frequency of the waves getting quicker or is it getting slower? Okay, and it's easy to understand when it comes to sound because you've seen it, or well, you haven't seen it, you've heard it through, again, police sirens, fire trucks, the tornado sirens. So it'd be a good idea to go watch that video and understand how it applies to sound, because we then see it with weather radar. And ultimately, where we want to go is with light. And you've got this red shift and blue shift. Red shift means that the frequency, okay, is getting longer than just that normal frequency. Okay. When the frequency is getting longer, that gives us a sign that the object is receding away from us. If we have blue shift, okay, the frequency is getting shorter. It's being compressed. That object is moving towards us. So all of this then applies to light emission. When we are able to see light scattered Okay, into its different components, we can see different beams. And each element has a unique emission spectrum. This emission spectrum for hydrogen is listed here. You can see we've got a bit there, a bit there, a bit there, and then there's a couple of lines here. We know that that's hydrogen's emission spectrum. We can see over here in this first copy that the lines have shifted ever so slightly towards the blue. And again, from our last slide, when it's shifting towards the blue, that means that that object is approaching us. So this line, okay, that hydrogen-containing object is moving towards us. This bottom line here, you can see where the arrows are pointing, are shifting toward the red. They're shifting down here towards the red side of the visible light spectrum. And again, what does shifting towards the red mean? It means that the object is receding from us. Okay, Lab 5, I will go over in class next time we have it. It is going to take you guys being responsible for a lot of this lab. We're not going to have time in class. You're going to have to, during work time or some other time that you have, come in and work on this on your own. Again, the next time we have class, I will go over that for us.